All right, so today we're starting into what is probably our longest unit of the year. It's going to take us effectively from here until the end of the quarter. And it's probably one of our heaviest hitting units too, in terms of some of the content. What is it? It's kinematics. So before we even jump into it, and before we even start sighing about things that you don't know, it's also one of the more exciting things that we can do. We need to understand, what does kinematics even mean? What's the root word in kinematics? Kinetic. Okay? And what does kinetic mean? Motion or movement. And if mathematics is the study of math, kinematics is going to be the study of motion. Okay? So we are going to try to develop the strongest understanding we can about how things move. Is that important, in your opinion, to physics? Absolutely. And which is why we spend so much time on this unit, to make sure we develop that very strong foundation in this, so we can springboard into other things. Okay? So in order to study how an object moves, we really need to quantify a couple of things. Well, we typically need some sort of distance measurement of some kind to know how far something travels. And we also need to know, well, in what time frame does it do that? Okay? So if we can figure out kind of a distance, how far, and a time component of how long it takes for that to happen, we can get a pretty good idea of what's happening on the motion perspective of that object. Okay? But as is the case with a lot of things, in physics, we're going to be very specific about how we're trying to understand things. So we're going to try to get even further than just simply a general distance measurement and time measurement. Okay? So in physics land, we need to be able to describe an object's motion properly. And in order to do that, we need to be able to specify an object's position at any given moment in time. We are going to start, in the context of this unit, with motion along the x-axis. Why? Because most things that we observe as a physical phenomena, motion can occur for us relative to us along an x-axis. Are there things that move on different axes? Absolutely. We have things that move vertically all the time. Okay? And we will get to that point, but we're going to start our discussion focusing on motion only along the horizontal axis. We will develop a solid understanding of that. Then we're going to move to where we have motion along a vertical axis. Then once we have a good understanding of that, we're going to combine both axes and have motions in two dimensions. Okay, but we are going to start with motion along the x-axis. So that's why an object's position right now is simply going to be labeled as x, because it's going to be a position along the x-axis. Okay? So an object's position is simply going to be the x or y coordinate where it falls along that coordinate grid. And again, we're one-dimensional motion right now. So we're going to stick to that x-axis. We need two specific points that we need to be able to label. An object's initial position, which we will simply label as xi, with I written as a subscript, and xf, for the final position of that object, with the f written as a subscript. So, while you're just writing those two simple things down, I want you to imagine for a minute, here in the front of the class, going wall to wall, that we have an x-axis. Okay? Where I'm currently standing would be the origin. Anything in this direction would be what kind of number? Positive, so that's to your right as you're viewing me. Okay? And then anything in this direction would be negative. So if I were to start here at the origin, and I walk 1 meter, 2 meters in this direction, and I want to know my displacement, okay? Well, we'd have to figure out where that is relative to the coordinate grid. Okay? This direction. And we need to know what those points are. Okay? Or if we're to move in the other direction, we need to know what the initial and final position are. And anytime an object changes position, like I just did from 0 to, let's say, the 2 meter mark, okay, it's going to experience what we call a displacement. Now, displacement is defined mathematically. Okay? The 3-barred equal sign that you see there, I'm going to venture a guess that most of you have probably not seen that before. Okay? It's just notation to say that this is a term that its definition is mathematical in nature. Are you going to write a 3-bar equal sign when we go to solve this? No. You will still use your standard 2-bar equal sign. But just know that this is a term, displacement is a term that is defined mathematically. Delta x is the variable for displacement. Okay? Now know that is delta and x. It is not separated from each other. Delta x is the variable for displacement. And mathematically speaking, what does delta mean? It's a change in whatever follows. And since we're talking about the change in position along the x-axis, right now that's delta x. Eventually, when we move to motion along the vertical axis, how do you think that's going to change? It's not going to be delta x, it would be delta y, because we would have a vertical position that would be changing with that. Okay? So, displacement is equal to our final position minus our initial position. That's the x final minus x initial. And we need to get used to, when we see that delta in physics, it's always going to be final minus initial. Always going to be final minus initial. Now, I have all this stuff that's written out here to the side about your displacement is going to be positive if this is greater than this or less than this. Just know if an object moves to the right, it's going to have a positive displacement. If an object moves to the left, it's going to have a negative displacement. So let's go back to my number line example. If I were to start here at the origin, and then I walked over to the 2-meter mark, we already said my displacement was what? 2 meters in the positive direction. If I were to start here back at the origin, and I walk to the negative 2-meter mark on that number line, what was my displacement? Negative 2 meters, okay, with the negative being the direction that we've traveled. Okay? But be careful about that, because what happens if I start here at the 2-meter mark and I walk over to the negative 2-meter mark? What was my displacement? It's negative 4 meters. Here's another one to get you. What if I start over here at the 2-meter mark, but I walk backwards to get to the negative 2-meter mark? What's my displacement? It's still negative 4. Nothing changes whether I travel forwards or backwards. It's about the direction that I'm traveling. Okay? So I want you, and I kind of throw that example out there on purpose because I get a lot of negative, it travels backwards. No, not necessarily. Okay? And positive doesn't necessarily just mean it's traveling forwards. It just means that the overall direction takes you there. Okay? So one last example, and not that you wouldn't get this, but if I were to start here at the 5-meter mark, and I walk to the 2-meter mark, my displacement is negative 3. So it really doesn't matter, do I start or finish on the negative side of the number line or positive side of the number line? It is simply a comparison of 2 points. Where do you start? Where do you finish? And believe it or not, that's exactly what we just did in vectors. Anytime we found a resultant, what were we doing? We were finding the difference between start and finish, effectively. Okay? So, that's displacement. Yes, sir. Go. Okay? Now, from here on out, we need to start the discussion about SI units. Anytime we introduce a quantity, we need to know what its proper SI units are going to be. For when we use that mathematically, it must already be in those units. Any measurement of distance, displacement, or even position is going to be measured in units of meters. Or if it's not measured in that, we're going to express it in meters. So meters would be our preferred way of trying to find that quantity. Are there times that we express things in the English standard system where we have inches, feet, and miles, that sort of stuff? Absolutely. Okay, but there are times that we need to go ahead and then do that conversion. We'll talk about many of those common conversions as we go throughout. But to continue our conversation from earlier in our test, before we start our lesson today, you have to know your metric conversion. And I think even more so than just, all right, when I go from meters to centimeters, I have to move the decimal point 2 places to the right. I need you to be comfortable to the tune of, I know. I see it and I know it without having to think about it. We might not be there yet, okay, but we need to be able to do these metric conversions. Because every day from here until June, you will be doing metric conversion. In addition to that, you'll also be doing some of the English standard to metric conversions. And so we need to be able to go between, right now we're starting with meters, we need to be able to convert that to centimeters, millimeters, kilometers. We don't have to worry about the we don't have to worry about like the deci and the deca and some of the other, those are the common ones that we need to know. Okay? And again, even today, we're going to be kind of going through a lot of it to figure out how do we go ahead and do those conversions. All right, so I'm going to use a baseball example to go ahead and drive a point home. Is there anybody in here that likes to play baseball? Anybody? Does anybody in here know how to play baseball? Yeah, since we don't have anybody that's really enthusiastic about playing baseball in here, you know, maybe I should choose a different example. Do you want to be an example for today? Sure. Okay, I appreciate it. As a lone person that maybe played an inning or two of baseball in his life, we'll go ahead and use Wes as our baseball player. Okay, so now this is totally hypothetical. Okay, so I want you to know, anything good or bad, it didn't actually happen. Okay. All right, so Wes is going to play baseball, which maybe he's done once or twice in his life. Okay, so he's going to come up to the plate, and wouldn't you know it, in his hypothetical example, he hits a home run. Good job, by the way. I'm proud of you. Good work. Okay. Now, I know that this may be defined a little bit differently, but in general terms, what's your starting position?
Home plate.
Home plate. Now I know you can't stand on home plate and hit a home run. What happens? You're called out, okay? If you stand on the plate when you make that hit. But to kind of help us with what we're dealing with here, generally speaking, Wes is going to start at home plate. Now, he hits the home run. Wes, what do you do when you hit a home run? So you yell yeehaw and then what?
Run around the base.
Okay, you're going to run around the bases. Okay? So he's going to do it slowly. And to help us out with the physics side of it, he's actually going to be even more specific than that. He's going to start here at home plate. He's going to slowly kind of jog his way down to first. Now, because he's very methodical, he's actually going to stop on the base, pivot at a perfect 90-degree angle, and then travel from there to second base, pivot right at that moment, another 90 degrees, travel down to third base, and then pivot once more and travel home. Now, Wes also knows the distance from home to first is 90 feet. I know it's not metric units, but work with me on this. Okay? And it is also 90 feet from first to second, from second to third back to home. Now, Wes had an opportunity to go around the bases. What is his final position? Home plate. Okay? Now, with that information, what is the total distance that he ran, or in this case jogged, around the bases? He went 360 feet. And thank you, Wes, for pivoting at 90-degree angles and stopping directly on the bases so we could know the exact distance that you just ran as we went around. But what was his displacement? It would be 0. Let's keep consistent units. 0 feet. Why is his displacement 0? Because in displacement, we only care about 2 points. Where do you start? Where do you finish? We care not about the path that you take with displacement. We care about only those 2 points. Game's not done yet. Wes comes up to at bat number 2. And wouldn't you know it? It's hypothetical. Didn't actually happen. Wes hits home run number 2. So he starts at home plate again, but this time he actually gets a little excited about it. Okay? So he starts here at home plate. He runs past first base, kind of out around his friend that's playing second base, saying nanny nanny foo foo. Comes back, hits second base, comes over here, gets a hot dog from the stands. Okay, then comes, does some cartwheels down the line, hits third base, comes over to give Coach Plank a high five, and then comes back here, back to home plate. Did he travel a greater distance that time around? Yeah. Absolutely. What's his displacement? 0. Okay? Because in displacement, we care not about the path that you take. It is simply about where do you start, where do you finish. By the way, good job, man. 2 home runs in 1 game. Okay? We won't tell him that you struck out in the next at bat. Yeah?
Isn't that like the first question on the quiz? So the
but the answer for the one on the quiz was that the displacement would be smaller, so why would that not be the same? So it overran the base, but ended up with the same place.
Okay, because in the total distance, you actually measure the total path that you take. So, but in terms of displacement, even a resultant displacement, as we did, it was only a comparison of start to finish. So from a value perspective, let's take this last example here, or any of the examples. Hey, the total distance that Wes would have run around the bases would be far greater than his displacement. Okay? Because distance does care about the path that you take. Displacement does not. Okay? And believe it or not, even though you think that it may be more specific, we care more about what the displacement would be. Okay? So let's do 2 quick sample problems. And I need to put a disclaimer out there. These are easy problems. You will not work ahead because you're going to make a mistake on one of the easiest problems we're going to do all year. So please don't work ahead. All right, we have a marble that's going to roll alongside a meter stick. It begins moving at the 98 centimeter mark and stops at the 87 centimeter mark. Question?
Yeah, when we're writing down the formula, do you want us to write the
2. We'll get that and our next step. So Cole, you're actually helping to answer my next question. What is the first thing that we need to show for any word problem as part of our solution? The equation that we're going to use for this. Okay? So, step 1, we're solving for displacement, so we need the equation rearranged for displacement, which is pretty easy. Okay, so we'll just put our x final minus x initial is equal to delta x. That is our displacement equation. All right, so now we need to take a look at the data in the problem, and we need to figure out what is our final position. Okay? So I'll put this out to you as a class. What are we going to plug in for final position?
87.
Told you guys going to make mistakes. I will come back to something that was stated earlier. We need to ensure that our values are in proper SI units prior to substitution into the equation. Now I know some of you that are higher on the intelligence spectrum are going to challenge me with something in a minute, and I'll address that in a minute. But 0.87 is our correctly converted value. Now I know you're going to get what x initial is going to be. 0.98. You can do this in your heads. Negative 0.11 monkeys, bananas, gallons of milk. No. Meters. Thank you, though. Thanks for the correction and for the help. Now, that is our solution here, and that is correct. Let's check it from an answer. Is it negative because it rolls to the left? Yeah, absolutely. Okay, it starts at the 98 centimeter mark, goes to 87. It does go to the left on our meter stick. Okay, does it travel 0.11 meters or 11 centimeters? Absolutely. It is correct. Okay, but it's always worth checking our answer and evaluating it versus the problem. Now, here's the argument that some of you were going to try to make. But Talbot, come on, man. I can go ahead and do 98 centimeters and 87 centimeters, 87 centimeters minus 98 to get negative 11 centimeters, and then do a conversion. On this problem, you're right. But this would be the only problem all year where that would be the case. Because this displacement equation is the only one that I can think of off the top of my head that is going to have everything in the same units. If we had an equation that is incorporating dissimilar unit-based variables, things that are measured in different quantities, it wouldn't work for us. Okay? We have to make sure, starting now, that anytime we do any substitution, everything we plug in has got to be in SI units. The good thing for that is, I do not ask you, you've I think heard this before, you do not need to plug in your units as part of your substitution. It is assumed that when you plug in values into an equation, those values are already expressed in the proper SI unit. So right now, the only thing we've really talked about is distance and displacement. Okay, but that's what we get for our sample problem A. Questions? All right. Quick question. How many of you in here, and please be honest, I do appreciate honesty, how many of you in here do not know what a lazy Susan is? It's okay. It's okay if you don't know what one is. I appreciate the honesty to the handful of you. Yeah, like it's one of two things. One, like if you have like a patio furniture set, like you sit outside, you know, and there's a little circular thing or something like that in the center, kind of near where the umbrella would be, and you can put your ketchup on there and just kind of spin it around to get it to someone on the other side of the table. Or if you have kind of like those corner cabinets that have the things inside, you can kind of store stuff in the back without having to try to shove stuff over things, under things, back in the corner, you know what I mean? Okay, those are lazy Susans, okay? So, a lazy Susan is spun 3 times. A container of parsley flakes travels around a circular path having a radius of 6 centimeters. We want to know 2 things. We want to know the total distance traveled, and we want to know the displacement of our parsley. Now, here's the thing though. I'm fairly confident, maybe 80% so, that you have never in your life been exposed to the magical parsley flake equation. Anybody in here know the magical parsley flake equation? No? So guess what? We get to make one up. Okay? We have to use some mathematical modeling here to help us out. Okay? So in A, when we need to find the distance, which by the way is represented by the lowercase letter d, not delta x, to separate those two a little bit, we need to actually come up with an equation that's going to help us to find the total distance our parsley flakes travel. Now, thinking back to math, is there some equation that we know that might help us to understand the path these parsley flakes travel as they go around the outside of a circular path? The circumference equation would help us. Okay? What is the circumference equation? Okay, many of you have learned it. I'm going to leave some space here. Many of you have learned that as 2 pi r, which is perfectly fine. I grew up in New York, where I guess our education systems were a little bit different. I learned it as pi times diameter. So that's just how I learned it, and that's okay. Whatever you do is fine by me. It means the same thing. Okay? How many times around this circular path do our parsley flakes go around? 3. Would this be a decent mathematical model for this situation? Absolutely. Okay? So let's do our simplification. At the same time, we're going to do our substitution. So 6 times pi times our radius. What are we going to plug in for radius now that we're all intelligent human beings? Thank you, Allie. 0.06, not just Allie, but Allie and others. And we can go ahead and figure out the total distance traveled. What are we going to plug in for pi? Use the pi button. Do not do 3.14. Okay, for those of you that have a TI 83 or 84, okay, it is directly above the division. I believe it is the second, and then the little caret that will get you there. Pluggy chuggy. And Anaya, when you get a quality response, let us know. 1.131 bananas. Meters, thank you very much. Okay? Positive or negative? It's actually neither. It's distance. It has no directional association. Okay? It's just 1.131 meters. That's it. Is that a reasonable response? You know, 6 centimeters isn't a huge radius, but it travels around that. It goes around 3 times. It's reasonable. It's not like we get 4,000 meters as the distance our parsley flakes travel. Okay? So that's a respectable distance, and that's actually what we should get for this. For part B of this, what is the displacement? What is it? 0 meters. Good. Why is it 0? Its finishing point is exactly where it starts. In the same way Wes can run around some bases, here parsley flakes end up exactly where they started, so the displacement will be 0.
For
problem like this, we have to write out a formula for?
No, because it's not a defined point for given data. So I'm fine with that as an answer. And certainly as part of discussion's sake, you should be able to say why that's the case. Okay, so simply to say, now I'll be honest, you're not going to have an assessment question that's that. Okay, all right. Now we're going to take a little bit of a jump here, but I need you to understand that even though we're going to talk about something that's going to initially seem like it is completely removed from what we're just talking about, it's actually directly related. Okay, we need to talk now, switching gears a little bit, about position versus time graphs. Okay. There's a very specific way in which we're going to make these graphs, and we're actually going to be able to generate some more data based off of what these graphs have to offer. So, okay, important relationships can be discovered from graphs. We're going to plot a sample position versus time graph to analyze stuff. You can go ahead and start to write down step 1 of our 4 steps in this process. Okay? That is step 1. Okay? There are 3 components to step 1, which I simply just call label, label, label. We have to label our x-axis with time, with its appropriate units. Now is when we get to talk about it. What are the SI units for time? Seconds. That's how we express all values of time. Okay? You're going to label the y-axis with position. We've already talked about this. What units are we going to use for position? Meters. Okay? And then lastly, as we've already kind of talked about in some of our previous graphs, we're going to title this simply just position versus time. We do not need the elaborate, the effect of this on Thursday when it's raining and it's 70 degrees outside. Okay? Just give us a very simple position versus time title. That's all we need for this graph. Step 2 is probably the most important in all graphs. We need to figure out an appropriate scale for each axis. And our goal is to make this as large as possible. Now, for those of you that haven't figured this out yet, I'm fanatical about details. Okay? On graphs that you have where we have data that I provide you, I typically go as far as to provide you a very specific grid to use. Now, in experimental data, when we're collecting quantities as part of lab, we can't accurately predict the number of spaces that we need. But we are always going to try to space this out as large as possible. I know I kind of threw out there a rule of thumb about 2/3 or more of an axis, and we really should try to use the most amount possible. But at a minimum, we really need at least 2/3 to 3/4 of an axis. Okay? Step 3, we will plot our data points neatly and connect them with a smooth line. Smooth line meaning use a ruler. Not the side of your calculator, not the side of a binder, not Jackson's hair. Okay? Just go ahead and make sure we use a straight edge ruler to create our connections between our data points. Step 4, calculate the slope of the segment by using this. I'm okay right now with us calling slope m, as to be consistent with what you've done in your math class. But most importantly, we need to have it as x final minus x initial over t final minus t initial. Which, yes, would be, okay, rise over run. Please do not do y2 minus y1 over x2 minus x1. You will confuse yourself. Why? Because we are graphing x, position, on our y-axis. You will goof that up if you do that. So please, we'll be consistent. It will be x final minus x initial over t final minus t initial. Preguntas? Questions?
I got a 60 last year, so sorry that you didn't do it.
All right. Now we're going to go to a sample graph and do this together. Not the one that has the chicken up top, but the other one. Okay? That's on the other side. As with many things, I know it's going to seem like an easy task. Do not start, because you're going to make mistakes, as some of you already have. Follow us and follow the process, please. Okay? So we have a sample position versus time graph that we are going to do together. You see on the left-hand side, you have a data set that we are going to use. On the right-hand side, we have a happy little grid that we're going to use. Below all of that, because I care about you, is I've given you a happy little checklist for you to use. So when we've done things, we can actually go down there, check them off, and get a true sense of accomplishment like we've actually done something today. So when you get there, you're going to get that warm, fuzzy feeling and say, I've done something good today. Because in physics, that's what we care about. We want to make sure that you get that warm, fuzzy feeling and that sense of accomplishment. So we're going to do that today. Sound good? All right. Sebastian, why don't you start us off here? What is the first thing that you're going to do with your graph?
Label the axis, the axis.
Which one would you like to label? You would like to label the x-axis. Where is the x-axis? Are you sure? Okay. You are correct in the fact that we should do this, but we have an evaluation to make. Look at your data. It's all positive data, correct?
Yeah.
So what quadrant does this data need to be in? The first quadrant, which would mean that our x-axis is going to be along the bottom. But we can't just assume that's going to be every graph, because even next class I'm going to throw one at you that's not. Okay? So we need to take a look at what we have. You will never have a position versus time graph, or any graph versus time, that's going to be quadrant 2 or quadrant 3. Why? Can't have negative time. If you legitimately figure out a way to get to negative time, you can contact me, we'll go in business, and we'll make billions of dollars. But until then, we will not go backwards in time. We will not go back to quadrant 2 or quadrant 3. So our options are 1 or 4.
So what would the x then be on the top?
Correct. That if we were the fourth quadrant, because we would have to have negative position values, x-axis would be up top. So that's why I kind of caution you. We have to figure out where that would be. Okay, is it going to be the top or the bottom? Here it's going to be the bottom. But before we even put anything on paper, we still have to put our scale that would be in there. So leave some space. Okay? So down below here, we will leave some space, and we will put the label that Sebastian was going to put. And that is going to be time in units of, I think you said it, but seconds. Okay? And we do leave that little bit of space there so we can go ahead and do that. All right? What's next? Santana, what do we want to do? We'll label the y-axis position in meters. Absolutely. So leaving some space, position in meters. Good. Nate? What's next? Not yet.
Label the actual graph.
We need to label, well, we need to put our title up top, which is simply going to be, and we can put it as close as we want because we're actually not going to go to that point, position versus time. Now, everyone, once you're done with that, you get to go down here, put a happy little check mark next to step number 1. Look at you guys. I can see the sense of accomplishment already. We've done something today. Good work. Okay? Maddie, what's next? Good. Which one do you want to start with? Okay. Maddie would like to start with position. That is perfectly fine. Here's what we need to ask ourselves, even though we already know the quadrants. What is the minimum inside of that data set?
0.
0 in this case. What is the maximum within that data set? 1200. Because we're doing position. That was Maddie's choice. That's perfectly fine. We know that 0 is going to be in our origin, which is going to be in the lower left-hand corner because we're in quadrant 1. We're going to have to figure out a spacing called graduations. We're going to figure out what the graduations are going to be to take us from 0 to 1200 is the number of lines that we have. Now, we do not count this bottommost line. Why? It's 0. So not including that line, we're going to count up the number of lines we have going all the way up. And how many lines do we have? There are 24, as if Talbot almost magically selected the exact number of lines that we needed to make a perfect graph. So do we think that we could space out 1,200 meters and 24 lines effectively? I believe we can. So that means that each line would be how much? 50. And that means that we're going to label every single line, right? No. No. Please don't do that. Okay? Why? That's going to be such a mess. Trying to figure out what's going on, figure out what's where. Do not make it that complex for yourself. Now, even though every one would be 50, can we just simply do every other line as 100? That would be a pretty good way to do it. So let's do that. So 0, skip 1, 100, skip 1, 200, go all the way up. And what we should find is when we get all the way to the top, we should hit our 1200 mark based on the scale that we've set. Sebastian, I appreciate you volunteering to help us out with our x-axis. What's our minimum in our data for our x-axis? And what's our maximum? 1800. Now I know I've kind of given you an easy data set to sift through, but we do need to figure out what's the minimum, what's the maximum. We need to make sure we can express all those values. Now, not including the first vertical line all the way to the left, how many lines do we have going across? There are 20. Now, it's not going to work out perfect to put our last data point on our last line, but can we get very close?
Yes.
Absolutely. So that would mean that every line would be 100, but same way, we're not going to label every line because that would just be a big mess. So 0, skip 1, 200, skip 1, 400, and go all the way out. So that should get us to 2,000, which is very close to our 1,800 and our maximum in our data. And when we're done with that, we get to go ahead, check off another box. Really feeling good about ourselves at this point. Yes, sir?
Do you have to label units all the way to the end?
No. That's half the point of what the label is. One, it tells us what type of quantity are we measuring. And then in addition to that, that's why we put the units there. Because this down here, the time in seconds and the position in meters gives us the label. Those individual graduations should not have units with them.
Oh, that's not.
Okay, I'm sorry, I misunderstood your question then.
So if the graph, like, let's say at this point, don't go up to the very end, you still have to label like number like let's say go to 800, but we get up to 2,000 graphs.
You should label out to it.
Okay.
Okay? It's okay that we exceed our maximum value, in this case on our x-axis. It could be on both axes, and that's fine. We just want to get our maximum data point as close to the edge of that axis as we can. Now, it might not be our final point, which in this case it is because it's time. Okay? But we don't necessarily have to get all the way as our final data point. It's just whatever the maximum is. Because let's say, especially in terms of position, what if our maximum position didn't come at the beginning or end, as it does here? Okay, it's somewhere in the middle. We just need to make sure that we can get to that point on the graph without having to kind of jerry-rig our graph by trying to add a row or something like that. I see that, and that tells me we haven't done a good job of setting our scales. Okay, so let's set the scales first, then we'll go from there. Okay? All right, step number 3, we're going to do on our own because I believe you are intellectual human beings. Okay? Follow your data set. Make sure we're plotting things according to the correct axis. Okay? But you're going to plot your individual data points, then connect everything using a straight edge ruler. should find as we're plotting our data points is that we're going to get 3 very distinct and constant sloped line segments. Once again, we have those line segments, the data points set. Next, we'll use our straight ruler to do that. Not all graphs are going to work out as cleanly as this one has. Clearly, just as our kind of sample problem, the goal was just to kind of give us a nice, simple sample that gives us some data to work with. When you are done plotting your data, you can go ahead, go down to your happy little checkbox, feeling yet even better than you did before, because you've done another step. Okay, I do appreciate the fact that people are still not working ahead. I really appreciate your effort to kind of just hang tight. Hopefully we've made ourselves, or at least working on the closing stages of plotting our data. Before we go on to the last step, this last step is not a requirement for all graphs. Okay? It is something that I need to get us start thinking in terms of today's sample graph. But if all we needed was just simply to create a graph, these are the 3 steps that we need to do. Okay? Always have everything labeled. Okay, set up the graduation, set up the values across each axis to make sure we can spread out as much as we can. And then plotting our data. And every graph that I'm thinking about in this class is a line graph of some kind. And we're not creating bar graphs, we're not doing pie charts, we're not doing that other stuff. Okay, so we're going to connect our data points once we get there. All right, I need everyone to stop for a second because we're going to do this together. I want everyone to be together for this. Okay? In the calculation of slope, okay? Well, this is an equation we'll have to do. So step 1, we need to write out our equation. Our slope, which I'm okay still having as m, x final minus x initial over t final minus t initial. Now, in my many years of teaching physics, okay, I've seen many students kind of make a certain mistake. And it ends up being the association of the correct position with the correct time when it comes to this calculation. So I'll tell you what I do, and then you do whatever your little heart desires. Okay? But I think that what I do is helpful for many of us. Okay? So what do you think is more helpful to look at, the graph or your data? In this case, I would say the data for most of us. Why? Because if we goof on the graph or we do something with that, okay, it might be a little bit hard. The other thing is, we can remove all interpretations because we have raw data. And we know what the exact values are. We should use that data. So let's take a look at this first line segment. Okay? Obviously, where is our initial data point? It's at the origin at 0, 0. Okay? At a time of 0, a position of 0, which it doesn't always have to be that way. Very few graphs actually start at the origin. Okay? For our first line segment, where is our final data point? At a time of 600 seconds and a position of 1,200 meters. Okay? Here's what I do. And again, you do whatever you want, but we do have to get this association correct. I typically identify what is the initial position and initial time. In this case, well, that one was easy. At a time, look at how I'm doing this. At a time of 0 seconds, we are at a position of 0 meters. At our time of 600 seconds, we're at a position of 1,200 meters. Now, we should not even need to touch our calculators for this. 1,200 divided by 600 gives us 2. Okay? Now, that's not it. We're not done yet. What are the SI units for position, or in this case even displacement? Meters. What's our SI unit for time? Seconds. So we effectively have displacement divided by a duration of time, which gives us units of meters per second. which is the SI unit for, in this case, an average velocity. Now, I don't expect us to go much deeper than that for today, but do understand that that's what it is. It is an average velocity that we just found. Okay? Now, I know it is a straight line, and therefore, we have a constant slope of 2 meters per second. So at all points along that line, the velocity is 2 meters per second. But we're, next class, going to take a look at graphs that are not necessarily straight lines. We can still apply the same concept to. So here's what I'd like for us to do. Just take another minute or two, calculate the remaining 2 slopes. Okay, so let's do that. Same way. Do you need to show your work? Yes. All right, so we're going to go ahead and check our slopes that are on the board. 1, I do appreciate those of you that put your responses on the board because, yes, we did follow what we need to do. We need the equation. We need the substitution. We need the answer with appropriate units. Even though I know everyone in this room understands that is a 0 slope for our second segment. Okay, prove it. How do we prove it? Our position does not change over the duration of time. So the physical motion of that would be something that's not moving. If it's staying in a constant position over time, it is not going to be moving. Okay? Then we get slope number 3, which we know is a negative slope. Negative 1 meter per second would be the average velocity for that duration. Okay? So any instance that we find the slope between 2 points on the data set, we are finding average velocity. Okay? Real quick, let's all flip to the back because I want to describe what is going to be due for next class. And we're going to spend the time remaining today to work on that. We have our chicken graph that we are going to do. Now, I'm sure that you have heard the phrase at some point in your life, running around like a chicken with its head cut off. Today, we are going to plot the data of said chicken. Okay? Now, you will notice that the position data is a little more erratic than what we had from our sample problem today. Why? Because chickens don't just necessarily run in nice, clean data sets when they do not have a head. Okay? So we're going to go ahead and we will plot a similar graph in a position versus time graph, setting up appropriate scales, getting those data points. Down below, you are asked to calculate some average velocities, okay, between 2 values of time. Here's something that I do need to kind of prepare you for. Unlike the sample graph from today, some of those average velocity calculations are not going to be from consecutive data points, and that is okay. You will be finding the slope between 2 data points that the data might be doing all sorts of stuff in between. That's okay, because we're just finding an average between whatever those 2 points in the data are. So with what we had on the board, I had asked you to find the slope of predetermined line segments. That was pretty easy. We just showed the endpoints and worked from that. And with what you have, they do not use the graph. We have to use our raw data to figure out what that's going to be. So what is going to be due for next class? The completed chicken graph with the position versus time graph itself and the average velocity calculations that come below. Sound good? All right, let's use our time productively and let's get as much of that done before we go.